Okay, so 10.1 is really just going to be a continuation from chapter 9. So we're still going to be doing, and actually chapter 8 too, some hypothesis tests, some confidence intervals, but this time instead of one sample, we're going to have two samples. Nothing changes except for maybe how you check a couple of the conditions, the name of the test or the confidence interval, and then the equations. But the steps are all going to be exactly the same. At this point, like I hope you're starting to get a little bit comfortable with this inferential statistics idea. We only really have one different type, sort of two different types of hypothesis tests left after this. So we're getting really close to the end here. I find these to be kind of fun, kind of fascinating. So I hope you're enjoying this as well. So the first thing, excuse me, some notes on sampling distributions with two different populations. Lots of good stuff there if you want to read through it quickly. Basically, they say if you have two normal populations, then when you combine them, I don't think if you have a normal population, but really you just want to look at the end one. The end one has to be the one that's normal. So we'll talk more about that when we get to the next one. Your shape, there's how to test whether it's approximately normal. So it's still the n times p or the n times 1 minus p. Those have to be at least 10. Sampling distribution, the center is going to just be your p1 minus your p2. And then your spread, there's your formula right there. That's your standard error as long as no more than 10% of the population is being used. Okay, so for confidence intervals, there's your conditions. So we've got random, we've got 10%, we've got large counts. There shouldn't be any surprises. Again, if you're unsure, you would go over to your reference paper. We are in the proportions section 2, sample this time, estimate. Here's going to be the name. Here's your formula you're going to use, and then there's your conditions. There's the formula. Your z-scores, again, we've already listed these, but you could have a 90%, a 95%, or a 99. Those ones you should have already jotted down, which, by the way, while we're talking about that, they actually are in the reference paper. If you scroll ahead in your reference paper to the, I think it's table B, it's the T distributions, but at the very bottom, it does give you the z-scores. So if you notice right here, there's your 90% z-score, there's your 95%, 98%. So they are in your reference paper as well. I think I've said this before. Your reference paper is really very, very handy to have. Okay, so here's an example. So the question is, are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers between 2005 and 2006, 19.5% showed some hearing loss. And they just want to know, basically, has the hearing loss among teenagers changed between those two? Now, hopefully you can see here where this is different than the previous ones we did. We have two different populations here. You've got a population of teenagers that lived between, or that were teenagers between, hopefully they're still living, between 1988 and 1994, and then another sample between 2005 and 2006. So two distinct populations, and that's why we have a two-sample test here, because you've got two very, very different samples. Your standard error, I did do that. I don't know if I did this exactly in steps. I did. I don't know if I showed all of my work, so sorry about that. Let's see here. Maybe by chance, did I put it over here? Yes, right there is your standard error. So I didn't include that on the slide, but that top line right there would be the standard error. So you would just do your 15% times your 85%, and that's 15% times 1 minus 15% over the 3,000, plus the 0.195, which was the 19.5% times 1 minus that over 1,800, and then you add those two quotients and you square root them. And that's where I got my standard error from. So that's standard error right there. I don't know why I didn't include that on the slide. That's down here in this section. And again, to interpret, if you're to take many, many samples and the typical distance from the average difference in proportions from 1988 to 1994 in 2005 to 2006 is that 0.0144. For part B, use the results to construct and interpret. I did go up here, you can read this, but I did do the whole state plan do conclude. So here's my state. Make sure you state what you're estimating, which is P1 minus P2, and that's the difference in the proportion of teenagers with hearing loss and 95% confidence. Here I named my test and I checked my conditions. This one here, most of them are the same, 10%, you have to check both of them. So we had to assume there's more than 30,000 teenagers between 1988 and 1994, and there's more than 18,000 between 2005 and 2006 for that 10% condition. And then your normal large counts, you have to check 4 things this time because you've got P and then 1 minus P. So they're all right there, and since they're all greater than 10, you can assume normality. Now, jumping down to part B, it said to construct it. So this would be my P hat 1 minus my P hat 2, and since we're using a 95%, there's my z-score for 95%, and then that's times that standard error. Type that on the calculator. There's my confidence interval. And then this part right here is the conclude part. So we are 95% confident that the interval from negative 0.07 to negative 0.02 contains a true difference in proportions of teenagers with hearing loss between there. Since the interval does not contain 0, you do have convincing evidence that the proportion of teenagers with hearing loss has changed. So since 0 is not included, they are not the same and they have changed. Because it's negative, we can probably assume that it's actually gone up because that means that the proportion from 1988 to 1994 is a smaller number than the proportion from 2005 to 2006. Okay, and then very similar, let's do a hypothesis test. I think we do the exact same question, but with a hypothesis test. So this one right here, you're going to just use your null is just P1 minus P2 equals the hypothesized value, which for this class here, I've literally never ever seen a difference other than 0. So you can just start your null with P1 equals P2. To me, that's the easiest, but just know that that does come from this section right here, where this would be equal to 0 because eventually we're going to have to put that into the formula. So just know that the difference between them when you're hypothesizing is 0. Conditions, no surprises there. You've got your random, you've got your 10%, and then you've got your large counts with, again, 4 of them that are there. Here's your formula. Now, this is a little bit different. So if you look in this section right here, we've got this thing called P sub C. So this one right here is not like P hat 1 or P hat 2. It's PC, which I like to call the combined proportions. So how do you find P sub C? So to find P sub C, you find your number of successes in your first sample plus the number of successes in your second sample all over the number in your first sample plus the number in your second sample. So basically you're just combining all of the successes, all successes over all samples. And that gives you your P combined. And I'm going to show you how to do that in just a moment. But that's what goes in the denominator. So if you notice there, it says P combined times 1 minus P combined over N1 plus P combined times 1 minus P combined over N2. That's that 0 right there that I was talking about. It will always be there, so you don't need to worry about anything other than 0 being there. You could actually put that right on your reference paper. So when you're looking at excuse me, the reference paper here, this P1 minus P2, this section right here, that will always be 0. So if you want to change that on your reference paper, you could. That little section right there will always be 0. Okay, so let's go ahead and do an example. So this is the same example that we just saw. So it's with the teenagers and the hearing loss. Quick thing, you need to label what everything is. So I'm calling P1 the proportion of teenagers with hearing loss in 1998 to 1994. and P2 is the proportion of teenagers with hearing loss in 2005 to 2006. So my null is that there's no difference. Remember, null always means no difference. That means the proportion from the first sample would be equal to the proportion from the second sample. Now, what we want to look here is it says, do these data give convincing evidence that the proportion has increased, which means P2 would be greater than P1. So that's where my alternative comes from. So again, in this state, make sure you've got your alpha level, what your parameters are, so your P1 and your P2, and then what your hypothesis is. In the plan section, there's the name of my test. We've already checked all the conditions, so I don't need to do that again. So this is how you find P combined. It had said that 15% showed some hearing loss. So that 450 right there, that came from that there were 3,000 teenagers in the study, and 15%, so times 0.15, that would be equal to the 450. And then the 351 was from the second sample, which was 1,800, and then that would be times 0.195. And then that would be the 351. So you just take the proportions. It's the same time, the n times the p. You've actually already found that. And then that's over the sample size, so 3,000 and 1,800. Just make sure you remember your order of operations. That gave me that P combined. Now, I know it's kind of hard to see, but there, I don't know if I could, I don't know if that's any better, but there's the P combined right there. So the 0.167, 0.833, that's 1 minus 0.167 over 3,000 and then over 1,800. They're exactly the same. They're just over the different sample sizes. And then the top is the difference in the proportions. So 15% minus 19.5% and then minus at 0, which I told you was always there. You type that in the calculator, you should get negative 4.05 using a normal CDF on the calculator. And then again, labeling that is the minimum. That's my maximum, that is my mean, and that is my standard deviation. That gave me the approximately 0 there. Notice that, how did I know to do that direction? I would probably go up here. I would put my new z-score on the chart, negative 4.05. If you look in the alternative, it's negative, so you shade in the negative direction. That chart, that drawing is actually very, very important, especially if you happen to forget to label things. I think the drawing would suffice for credit. So please make sure that the drawing is there. That's why I did to the negative 10,000 to the negative 4.05. Conclusion, since P is less than alpha, you reject the null, and therefore you do have convincing evidence that the proportion of teenagers is less than P2, which is the proportion of teenagers in that other year there. Part B is very interesting because it says Apple introduced the iPod. So can we blame iPods for the difference? And hopefully you all know that the answer to that is no, because there could be other factors that are influencing the hearing loss. iPod is not responsible for hearing loss, unless, of course, it was a controlled experiment and they were randomly selected and randomly assigned, which they were not. Last example. So this one is same type of example. This is to help employees stop smoking. Half of the subjects were given an incentive, while others were just encouraged to use traditional methods. They had 878 volunteers who were randomly assigned to one of the groups. 15% of the group that got the financial rewards had quit smoking, while only 5% in the traditional group had quit smoking. So we want to know if we have convincing evidence that the financial incentive helps people to stop smoking. So state, we wish to test the following. Remember, you have to have your alpha level. You need to name your parameters. So P1 is the proportion of employees who quit with the incentive, and P2 is the ones who quit using traditional methods. In your null, there's always that equal sign, which means that there's no difference, that the financial incentive did not help at all. And then in the alternative is that the financial incentive did help, which means P1 would be greater than P2. Plan, use a 2-sample z-test for P1 minus P2. That's the name of the test. Please make sure you always include the name of the test. Random, they were randomly assigned to groups. 10%, I did 10 times the 878, so assume that there are more than 8,780 employees, which it's GM, so there probably is. Normal large counts, there should be 4 conditions checked here. So 439, which is half of the 878, because it said half went to one group and half went to the other. So 439 times the 15%, 439 times 1 minus 15%. And then for the other group, 439 times 5%, and 439 times 1 minus 5%. And since all of those numbers are greater than or equal to 10, we can assume normality. Again, here is your P combined. So just as a review, how did I get that P combined? I took the 439 that were in the one group, and it said that 15%, so I multiplied that by 0.15, and that would give me the 65.85, which I did say before, but now that it's right here, you already found these numbers up in the conditions. So you can look to see how I got those. Same thing for the 21.95, and then it's over the total number of people in the sample, which was 878. That gives me 0.1. So again, I know it's hard to see. Let me see if I zoom in. If it's easier, right here, you have the difference in the proportions, minus 0, because that will always be there. Down here, you've got the 0.1 times 0.9, and then that's over the first sample size, which is 439, plus the 0.1 times 0.9, and that's over 439 again. All on the calculator, you get 4.939. And like I said before, the sketch is super important, so I'm going to put 4.939 on a normal curve. And then if you look up here in the alternative, there's a greater than symbol, which means I shade greater than. So then down here, this 4.939 will be my minimum. 10,000 is my maximum. 0 is my mean. And 1 is my standard deviation. And then done on the calculator, that gives me a very, very small number, which is approximately 0. So since P is less than alpha, we reject the null. P is small, we reject the null. Therefore, we have convincing evidence that the financial incentive helps people to quit smoking. So that's that. So again, best friend will be your reference paper because it's all right here, all of your stuff that you need. The names, the formulas, the conditions, just follow it step by step, and it should be pretty straightforward and simple. So that is how you do a confidence interval and a hypothesis test for 2 samples. The next video, which is 10.2, will be for means, again with 2 samples, and then I believe that finishes up chapter 10.